So, hello everybody. Today I'm going to present a general theorem for convergence rates in the probabilistic analysis of algorithms. And this is joint work with Ralf Neininger. So, as an introductory example, I would like to start with a binary search tree built from a random permutation of length n, here length 10. And as is well known, the first key is inserted into the root. This is number 6 here. And then the remaining keys are inserted into the right or left subtree of the root, depending on their values being smaller or larger than 6. So letting the tree grow step by step, we obtain this binary search tree. And now we want to analyze the number of nodes in this tree with a certain property. For example, the number of leaves, or the number of nodes with 2 children, or in this example, we denote by L0n the number of nodes with no left descendant. These are the red squares in the picture. And by L1n the number of nodes with exactly 1 left descendant. These are the blue squares. So the idea now is that these two quantities can be decomposed recursively in a very natural way, because to count the number of such nodes, we can just count the number of such nodes in the left subtree of the root, then count the number of such nodes in the right subtree of the root, and eventually add 1 if the root itself has the given property. So to formalize this, we now denote by I1n and by I2n the sizes of the two subtrees of the root. And as we want to study the two quantities multivariately, we denote by yn the two-dimensional vector consisting of these two quantities. Then, with this notation, we can write down a two-dimensional recursive relation for yn. So this is just what I described before. The total number of such nodes can be decomposed recursively by adding the number of such nodes in the left subtree plus the number of such nodes in the right subtree of the root plus this term bn here, which takes into account that the root itself can also be a node with no left descendant or with exactly 1 left descendant. So now, following a paper by Luc Devreux, it is easily shown that the mean and the covariance structure of yn can be computed exactly, and it turns out that everything is linear in n. Devreux has already shown that the univariate quantities here are asymptotically normal, and this is also true for the multivariate quantities, which means that if we normalize yn appropriately by subtracting its mean vector and by multiplying the inverse square root of the covariance matrix, then we have weak convergence to the two-dimensional standard normal distribution. So, however, in this talk, we not only want to show weak convergence, but we also want to estimate the rate of this convergence. And for this, I will now introduce a much more general framework, and then I will present a general theorem for convergence rates. So now here is this recursion we've seen before, where the original problem was split into two smaller subproblems of the same nature. And now our general setting is a much more general recursion, which is of this form here, where yn is now a d-dimensional random vector, k is the number of subproblems. As before, in is the vector of the subproblem sizes. So this is a random vector with whose components are assumed to be random integers between 0 and n. Then we have these square matrices A1 to AK, and again a d-dimensional random vector Bn. Okay, then we need the self-similarity condition here, which formalizes that the models in the subproblems are the same as the original model, and we need some independence conditions that guarantee that given the subproblem sizes, the subproblems behave independently. Okay, so this is the general framework we work in, and now I want to introduce the method of proof, which is the so-called contraction method, and which was introduced some 30 years ago by Uwe Rösler for the analysis of quicksort. The starting point of the contraction method is always this general recursion here we've seen before. And then we define the normalized quantities xn, as shown here, where mn is a d-dimensional vector and cn is a positive definite square matrix. So essentially we choose mn as the mean vector and cn as the covariance matrix of yn if they exist. In the one-dimensional case, this is just subtracting the mean and dividing by the standard deviation. And then the idea is that this recursive relation for yn can be transferred to the scaled quantities xn. If we just plug in the recursive relation for yn here and then rearrange the terms appropriately, then we see that xn can also be written in this recursive form, which is exactly the same form as before, but with modified coefficients. So these modified coefficients are displayed here. So here you see this modified recursion for xn again. And the idea now is that we show that these modified coefficients converge to some limit coefficients, AR star and B star. And then if we assume that xn converges to some limit x, then we expect x to satisfy this limit equation, where all terms depending on n are replaced by their limits now. So the idea now is to find conditions which imply that this equation indeed has a unique solution in a suitable subspace, and that in fact xn converges to this unique solution. So for this we can consider this limit equation as a map from the space of probability distributions to itself, such that the fixed points of the map coincide with the distributions that solve this limit equation. And then if we choose a complete metric such that the limit map has contraction properties in this metric, then Banach's fixed point theorem implies the existence of a unique fixed point in the appropriate subspace. And the idea is then to show convergence to this unique fixed point. So in short, the idea of the contraction method is to find conditions such that we can transfer the convergence of this coefficient, of these coefficients, to the convergence of xn to its limit x, where the limit x is characterized by this limit equation. However, in this talk, we are we not only want to show weak convergence, but we want to estimate the rate of the convergence. And for this, we now need some conditions that allow us to transfer the rates of the coefficients, so here measured in terms of LS norms, to the quantities xn. Here, the distance between xn and its limit x is measured by the Solotariev distance, denoted by zeta s. And I won't go into detail about the Solotariev distance here, but just have in mind that the Solotaryov distance is a complete metric on a suitable subspace, and that the convergence in the Solotaryov distance implies weak convergence. So although there are more popular distance measures as, such as, for example, the Kolmogorov metric, we make use of the Solotaryov distance because it allows us to derive a very general convergence theorem that is easy to apply and that covers lots of examples at once. So now here you see our general transfer theorem. The sequence xn is appropriately normalized as before and satisfies the modified recursion we've seen before. Then we assume that the rate of the coefficients is of the order big O of R of n. And we also need two technical conditions that guarantee that the subproblem sizes grow with n. So this is this condition here and this condition here, but they are usually satisfied in applications. Okay, then we have this lim sub condition here, which implies that the convergence rates of the coefficients can be transferred to the quantities xn. And this condition also implies that the limit map has indeed a unique fixed point on an appropriate subspace. Okay, if all these conditions are satisfied, then we can show that the Solotaryov distance between xn and its limit x, which is characterized by the limit equation, converges or is of the order big O of R of n as well. So this is our general theorem, but we also have a refined version of this theorem, which applies if the limit distribution is the normal distribution. So this is the refined version for the normal case. We now additionally assume that the limit coefficients satisfy that B star is 0 and that the squared limit coefficients are AR star sum to 1 almost surely, or to the identity matrix in the multivariate case. And then we see here that we need weaker conditions. So we have this additional factor 3 here in the exponent that doesn't appear in the previous general theorem. And this is the reason why this theorem often improves over the general theorem we've seen before by a factor 3 in the exponent. Okay, then the rest is almost the same as before. We have this technical condition, lim sub condition, and now we measure the distance to the normal distribution. Okay, so now that I've stated the main result, I would like to list some possible applications. So first, we can treat geometric problems that can be decomposed recursively. For example, the number of maxima in right triangles. So here Bai, Huang, and Tsai showed in 2003 that this number of maxima is asymptotically normal with convergence rate n to the minus 1/4 in the Kolmogorov metric. And with our refined version of the theorem, we can now kind of rederive this result for the Solotaryov distance, and we obtain the same convergence rate n to the minus 1/4 without much effort. So then we can analyze quantities of divide and conquer algorithms, for example, the number of key exchanges or key comparisons used by quicksort or by quickselect. And here we can rederive a result by Ralf Neininger and Ludger Rüschendorf from 2002, where they showed that the convergence rate in the Solotaryov distance of the standardized number of key comparisons used by quicksort is of the order log n over n. And with our theorem, we obtain the same convergence rate. So then, as a third large class of examples, we can analyze parameters of random trees. For example, the size of random M search trees or the size of random tries, the number of leaves in quad trees, or different path lengths in random trees, for example, in digital search trees, tries, and Patricia tries. So here, for example, if we now denote by yn the size, so the number of internal nodes of an M search tree, then Huang showed in 2003 that this quantity is asymptotically normal for m at most 26. And he also derived convergence rates for the Kolmogorov metric. And the rate is 1 over square root of n for m between 3 and 19, and becomes slower for increasing m. Now, with our refined version of the theorem, we can obtain the same convergence rates for the Solotaryov distance, but with an additional epsilon here in the exponent for m between 3 and 19. Okay, so now coming back to the introductory example, we can now use our refined version for the normal case to obtain the rate 1 over square root of n here in this example from the beginning. Okay, and now as a last example, I would like to show a theorem to analyze quantities that where the asymptotic expansion of the mean and variance include periodic functions. So this is often the case for quantities in binomial splitting processes, such as tries, Patricia tries, or digital search trees. Okay, we assume that yn is a sequence that can be decomposed recursively into two subproblems of binomial sizes. And we assume that the mean and the variance of yn is asymptotically linear in n with these approximations here. And then we can show with our refined version of the theorem for the normal case that the standardized quantities converge to the standard normal distribution with rate n to the minus 1/2 plus epsilon in the Solotaryov distance. So possible applications of this theorem are, for example, the number of internal nodes of a trie in the symmetric Bernoulli model, or the number of leaves in random digital search trees. Okay, this was the last application I wanted to give. Thank you for your attention.